The day I noticed the discrepancy in NASA's JPL Horizons database, I certainly wasn't hunting for mysteries. I was doing what astronomers do, tracking the movement of C 2024 S1 Atlas, an interstellar wanderer making its way through our solar system. For several weeks, I've been watching a particular value, the A1 parameter, which measures non-gravitational acceleration normalized to 1 astronomical unit. The number sat at 1.66 times 10 to the power of negative 6 AU per day squared. Elevated, certainly, but explicable if the comet was actively outgassing in predictable patterns. Then November 24th arrived, and without warning, that figure dropped to a quarter of its previous value, 4 times 10 to the power of negative 7 AU per day squared. No annotation, no technical bulletin, just a silent revision. In our field, this matters profoundly. These aren't arbitrary digits, they're the mathematical foundation for predicting where an object will be months or years from now. A fourfold change doesn't just adjust predictions, it rewrites them entirely. So naturally, I began investigating. I focused on one particular moment in this comet's journey. It's March 16th, 2026 flyby of Jupiter. This encounter matters enormously because Jupiter essentially guards the outer reaches of our solar system with its massive gravitational field. What caught my attention was extraordinary. The projected closest approach fell remarkably close to what we call Jupiter's Hill radius, that critical boundary where Jupiter's gravitational dominance gives way to the Sun's influence. This wasn't some minor footnote. This was a geometric alignment that demanded attention. Understanding the Hill radius is essential here. Imagine Jupiter sitting in a gravitational bubble, its Hill sphere. Inside that bubble, Jupiter's gravity reigns supreme, capable of capturing satellites or dramatically altering trajectories. Beyond it, the Sun's gravity takes over. Our calculations show the approach distance matched this radius to within 0.06 million kilometers, essentially within the margin of error. Given the immense three-dimensional volume of space this comet could have traversed, such precision seemed geometrically improbable. I compiled my findings into a comprehensive analysis and sent it directly to David Farnocchi, the astronomer managing the JPL trajectory solution. I anticipated what any researcher would expect: technical dialogue, perhaps some debate over methodological assumptions, maybe even respectful disagreement. What I got was silence. Yet within days, something did change. The A1 value dropped again, this time by a factor of 6, settling at 6.8 times 10 to the power of negative 8 AU per day squared. The database also reflected a fundamental shift in the underlying physics model. The original calculation assumed a steep sublimation curve r to the power of negative 7, or steeper characteristic of water ice behavior. The new model adopted a gentler r to the power of negative 2 relationship, more appropriate for carbon dioxide outgassing at 5 astronomical units. Here's what matters. This wasn't a small adjustment. This change fundamentally transformed the Jupiter encounter prediction. The new solution pushed the closest approach to 53.587 million kilometers. Conveniently, just outside Jupiter's gravitational sphere of influence. Has the comet's behavior actually changed? Obviously not. What changed were the mathematical assumptions we're using to describe it. But here's the fundamental problem. The comet doesn't negotiate with our models. It moves according to physical law, regardless of how we choose to characterize that movement. Science demands that we shape our models around observations, not reshape observations to suit our models. The challenge with this newer model becomes apparent when you examine the actual observational record. C 2024 S1's brightness increased far more dramatically than an R to the power of -2 model would predict. Hubble captured imagery on July 21st, 2025, revealing a remarkably complex coma structure. Recent work by Marshall Eubanks and colleagues demonstrated that luminosity, essentially a measure of how much material the comet is shedding, rose with extraordinary steepness as it approached the Sunday. Earlier research by Ken Zhang and K.L. Bottoms pointed to an R to the power of -7 luminosity profile within 2 AU of the Sunday. That kind of gradient is exceptionally steep, far exceeding what we see with water ice, far exceeding carbon dioxide. It suggests violent, explosive mass loss driven by volatile chemistry that differs substantially from typical solar system comets. When you calculate the cumulative momentum transfer using this steeper profile, the predicted trajectory brings you right back to that Hill radius alignment. So we have competing narratives, observational data suggesting one trajectory, computational models suggesting another. The critical question becomes, where does our trust lie? The answer has to be with empirical evidence, not with institutional convenience, not with assumptions that make calculations easier, not with avoiding uncomfortable questions. We follow where the measurements lead. And those measurements strongly suggest the R to the power of -2 approximation undersells what's actually happening. Here's the fundamental question we need to address. What physical mechanism is driving C 2024 S1's acceleration? We know it's not purely gravitational. We know it correlates with solar distance. We know the brightness profile is unusually steep. We know the outgassing rates are anomalous compared to familiar comets. The natural explanations are numerous. Carbon monoxide or carbon dioxide sublimation, explosive volatile release, asymmetric jet activity, fragmentation events, thermal stress fracturing. Some combination of these processes almost certainly explains what we're observing. Even if none individually matches the steepness we're measuring, we should remember that interstellar comets formed under completely different conditions, different stellar temperatures, different chemical abundances, different formation timescales. Their behavior may simply lie outside our current experience base. The Hill radius coincidence, while geometrically intriguing, may well represent a selection effect, one notable alignment among countless trajectories we might have observed but didn't find particularly interesting. We must guard against confirmation bias. We notice the patterns that seem significant and disregard the multitude of non-patterns occurring constantly in celestial mechanics. Yet I remain concerned about one aspect of this situation. If the revised JPL model was motivated more by reducing apparent anomalies than by accurately representing the comet's physical behavior, that's problematic. Science's foundation rests on measurement determining truth, not authority. Models exist to serve data, not the reverse. Let me be direct about something that might sound contentious. The mathematical precision of this alignment, if it proves accurate, merits systematic investigation. Not because I'm suggesting artificial origins, not because I'm proposing exotic explanations, but because statistically improbable events typically reveal gaps in our understanding. They often signpost new physics waiting to be discovered. Should the Perry-Jove distance genuinely match the Hill radius, and should this correlation involve non-gravitational forces we're still characterizing, then we've discovered an exceptional test case for understanding interstellar comet dynamics. It becomes an opportunity to refine sublimation models, to study unusual ice compositions, to understand how bodies from other stellar neighborhoods respond to our sun's radiation. Certainty will arrive in March 2026. Spacecraft observations from Juno or JUICE, combined with ground-based astrometry, will provide definitive measurements. History consistently demonstrates that physical reality doesn't accommodate institutional preferences. Whatever model NASA adopts doesn't alter C 2024 S1's actual path. The comet follows natural law, independent of human interpretation. In the coming months, we'll measure with precision whether this perigove distance aligns with Jupiter's hill radius. If it does, the scientific value lies not in speculation or dramatization, but in recognizing that unusual coincidences often illuminate physics we haven't yet properly understood. They reveal new chemical processes, new dynamical behaviors, new phenomena awaiting characterization. Our obligation as scientists isn't to proclaim certainty, it's to maintain openness. Openness to evidence, openness to model revision, openness to unexpected results. Science functions as an ongoing dialogue with nature, conducted through the rigorous language of quantitative measurement. Right now, nature is communicating something through C 2024 S1. Our duty is straightforward. Pay attention.